Okay. So let me check the recorder. It is recording. All right. So we are kind of almost done with the control unit here, which is kind of the last piece. Well, semi like that of the processor design. So at this point, what we have are several main components. We have talked about the ALU, which is actually doing all the work. Okay, because the ALU stands for the arithmetic and logic unit. Arithmetic refers to adding, subtracting, and comparing. Logic refers to bitwise AND, bitwise OR, bitwise NOT. Okay, those bitwise operations. So the ALU is responsible for doing the actual calculations. It looks like a funnel. We talked about this in class as well. Okay, it looks like a Y or a funnel, depending on how you look at it. It looks like a Y. The two inputs are on the top. The output is at the bottom. But the ALU can only do calculations. It has no way to store the result after the calculation. It also has no way to get the numbers to start the calculation. So that's why we talked about the register bank last time. The register bank as a whole basically has two outputs and one single input. Okay? So, and also a whole bunch of other control lines. Okay, but we are not going to talk about the control lines in this simplified picture. The two outputs can go into the ALU, okay? So you can actually do the calculations. The input can also be coming from the ALU. But that's not the only pathway, okay? Because if you do something like this, then where do you get the numbers to crunch on to begin with, okay? Because the registers need to start with certain numbers. So that's why, these lines coming in and out of the register, they also have to be connected to the data bus of memory. Okay, because otherwise you don't have any connections to the memory of the system. So we have a whole missing piece at this point, which is basically your RAM. Okay, so the data bus of the registers has to hook up to RAM as well, or the output or the input of the ALU can also be connected directly to RAM. Okay, so all of those pieces are missing at this point, but we do have the major components already done in our design. Okay. Then you also have to think about all the instructions, what you need to do with the instructions. Okay. In C and C++, you already know certain concepts like that. Okay. So I'll just give you one example. When I say char asterisk PTR semicolon, what is this PTR variable? It's a pointer. Okay. Now, what is a property of a pointer? What do you use it for? It contains the address of something else. In other words, at some point, okay, you will want to dereference a pointer. Okay, at some point in this case, you might have asterisk PTR equals quote C quote something like that, which means you're storing the ASCII code of C into wherever byte PTR points to. Okay, now that is important in this picture because it seems like I'm talking about really low-level processor design on one hand and talking about high-level programming language on the other hand. But why do you think these two concepts are related? PTR as a variable is storing a pointer. But how do I make use of that pointer? It means the content of one of the registers has to be able to drive the address bus of the RAM. So it can control which location I'm going to store or retrieve a byte or a word. Okay? So that is not discussed at this point. We'll talk about it. We'll continue to talk about it. But I want to kind of let you guys finish the homework assignment first. So what I'm going to do today is to skip that portion of the design. We'll talk about it on Thursday. And we'll skip that part for now, and we'll just kind of jump onto signed versus unsigned number today. Okay? But think about this a little bit, okay? Look at the processor design that I have already on the website. Okay, that's going to be changed. Okay, but it's a reference design, and you just have to think about how do we get some content in the register onto the address bus. Okay, because that's what we need in order to implement the concept of a pointer, or to be more specific, dereferencing a pointer. Okay, what about indirect jumps? Okay, does anyone know how to call a function indirectly? This is a C kind of thing. I'll give you some code here so you can see what I mean by that. All right, so let's see if you guys know what this is. What is this PTR?
The address pointer.
It's not a void pointer.
Address.
Okay, so okay, what is okay? Let me just this may give you a clue. VPTR in this case is a void pointer, okay, because it doesn't use any parentheses, so we kind of know this one already. A void pointer is actually more useful than most people think, because most people think, why do you need a pointer that points to void? Because you cannot do a single thing with something of the type void. Well, that's because we have to cast it so that it will point to something that actually has a type. That's the second one. The first one is actually a pointer to a function. Okay, this is a pointer to a function. How do I know this is a function? It's because of the list of parameters. Okay, the function returns void. So this FPTR is a function pointer, pointing to a function that has no parameters and returns a void. Are we doing okay so far? Were you guys exposed to this concept, in P360? It's unlikely, but it is a feature of C and C++. In fact, it is one of the more useful features. This basically, evolved to become member functions eventually. Okay, so member functions, particularly, what is the name of that member function? Virtual member functions. Okay, virtual member functions, basically evolved from something like this, but it's inside the structure. So you can basically say, okay, I have a structure here, X, Y, Z. It doesn't really matter what the name is. And then in here, you can have your usual stuff like, X as a data member. But at the same time, you can also have something like this. And you can also give it in, non-empty parameter lists. So in this case, FPTR is a member of XYZ. Okay, it is a pointer to a function. That function, whatever function it points to, returns a void, and it takes 2 integer parameters. Okay, so if you think about this, okay, you also need dereferencing, because now a particular member of this structure XYZ is storing the address of a function. So how do we actually start to execute and start execution at the beginning of the function pointed to by FPTR? That's also, in a way, related to what we are talking about here, because we have to basically be able to use one of the registers not only as a pointer to store something, but to continue execution at that place. Okay, so the connection between a register out of the register bank onto the address bus is necessary. Okay, is that okay so far? Kind of just in terms of concept. Okay, so we'll kind of work on this on Thursday, because I just want you to kind of think about this first, and then we'll talk about it on Thursday, and actually start to work on the mechanism to make this happen. So what we'll do today is we'll skip that part just for now, and we'll start on signed numbers. Okay, signed numbers is kind of an interesting topic, but at the same time it's kind of a not so interesting topic. The big question is, how do we store numbers that are representing negative values when you can only have zeros and ones? If you think about it, it's not a trivial question, because how do you write a negative number in base 10? So let's say we want to negate the value of 27. Well, the negation of 27, if you write it out using the natural way, it's just negative 27. Okay, you put a little minus symbol before the number, now it becomes a negative number. So we don't really have a problem of representing negative values when we're using conventional ways of using numbers. But inside the computer, there's no such thing as a sign. Okay, you cannot just say plus minus. Okay, they're all zeros and ones. All right. So if they're all zeros and ones, how do you represent a value that is negative?
Could you do 0? Yeah.
Sorry?
With a 0.
With a 0, okay, so with one of the bits, you can use it as a quote-unquote sign bit. In other words, if that bit is a 1, it is negative. If it is not a 1, it is non-negative, okay? So you can certainly use that way. So that means, if we're using a 4-bit number, how do you represent 5 as a negative number? in 4 bits. 5 has a 1 and a 4, so if you spell it out as a 4-bit number, what would be the zeros and ones? Where are they?
It would be 0, 1, 0, 1.
0, 1, 0, 1 in base 2. That is exactly what it is. This is basically the same thing as a 5. Okay? So if you want to represent -5, quote unquote, one way to do it, which is not the way that we are going to do it, is like this. Okay? That's one way to do it. Okay? It's certainly one of the more intuitive way to do it is to use the most significant bit or one of the bits to represent, the sign of the number. So in this case, we're saying, oh, this is a negative value. Okay? Yep.
Why wouldn't that be 13?
Because if you do it this way, the adder circuit that we have talked about, the subtractor circuit that we have talked about, cannot handle numbers like this. Because the idea is, if you add 5 to -5, what should you get?
0.
Would that happen here? 0, 1, 0, 1 in base 2 plus 1, 1, 0, 1 in base 2 is not going to give you 0, 0, 0, 0. So now you can actually build additional adders and subtractors that can take the sign into consideration. But that's going to cost you extra silicon. Okay, extra silicon, which means you need extra space on a processor die, is expensive. We don't want to waste silicon or waste die space unless we really have to. So it turns out there's a different way of looking at things that makes it possible to represent negative numbers without actually using this particular representation. Okay. So before we talk about that representation, how many people know modulus in math? Okay, modulus math in modulus number in math. Okay, so that means let's see here. Okay, so modulus. Okay, so let's say we are dealing with modulus 256 here. Okay, so if you're dealing with modulus 256. 0 is the same thing as 256, which is the same thing as 512, which is the same thing as 1024, and so on. Because you have to look at the mod 256 version of each of these values. Is that okay? Or not?
Oh, so you're saying that the modulus of what's going before the modulus of 256?
Okay, in a modulus math system, what you're dealing with is, after a calculation, you basically take the mod, with a base of everything.
You mean the remainder? So basically the mod just gives
Modulus is kind of the remainder thing, right?
Okay.
Yep. Okay. In other words, basically, everything that we do, there's an implicit mod 256 in it. Okay, so this is implicit to every single thing that we do. One way to look at this is to look at a number line. Okay? Pretty sure most of you, probably all of you, understand what a number line is. Okay? So what is a number line? A number line is a line that represents numbers. So usually on the right-hand side, it stretches out to infinity. On the left-hand side, it stretches out to negative infinity, with 0 in between here, right? Okay, so on one side, let's just say we're dealing with integers here. So we've got 0, 1, 2 on one side, we got 0, -1, -2 on the other side. Is that okay? So that's a pretty usual way of visualizing numbers and values. So now, instead of looking at the world as a flat world, it becomes a circle, a loop. Okay? All right, so when this becomes a loop, or when it becomes a circle, you're dealing with a number circle, not so much a number line anymore. So now it becomes a number circle. A number circle works kind of the same way. You have 0, 1, 2, blah, 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 okay? Well, you can look at it one way, and you can also look at it the other way. So let's say we're dealing with a 4-bit number. Okay, so if you're dealing with a 4-bit number, it will go from 1, 2, 3, and then this will be 4, right? 5, 6, 7, this will be 8, 9, 10, 11, 12, 13, 14, 15, and 15 is the largest unsigned value we can represent using only 4 bits. Is that making any sense? What happens when you add 1 to 15? You get 0, okay? So everything is the same thing as having to mod it with 16, right? So you can complete all kinds of calculations, but what you can actually store is a mod 16 type of value. Are we doing okay so far with that idea? Let's go through one calculation just to be sure that we understand that concept, okay? So let's try a particular calculation. So we'll try 1100 plus 0111, okay? So this is just an addition. This is also a quick test of how quickly you can do your binary addition, okay, without using your calculator. Okay, there's an implicit 0 here. 0 plus 1 is 1, 1 plus 0 is a 1 with no carry from the first digit. Oops. Okay. 0 plus 1 is a 1, 1 plus 0 is a 1 with no carry. 1 plus 1 is a 0, and it has a carry. 0 plus 0 is a 0. And then we have 1 plus 0 being a 1, 1 plus 1 is a 0 with an extra carry that cannot be represented as a part of the result. So what this means is 1100, which is 12, plus 0111, which is 7, is 3. Does that make any sense? Let's check it out. So the way you check it out is you start with 12. So 12, this is 15, 14, 13, this is 12, okay? And then how do you add 7 to it? You basically rotate it, or you just count and use a clockwise direction exactly 7 times. So what you do is you start with 12, and you say 1, 2, 3, 4, 5, 6, 7. So 12 plus 7 is in fact 3. But then you say, it doesn't make any sense to me. Well, because 12 is 12, plus 7 is supposed to be 19, right? What is 19 mod 16? 3. Exactly. So everything has an implicit mod 16 when you're dealing with 4 bits. When you have 8 bits, what is the implicit mod base? 256. What about 16 bits? 65,536, right? And what about 32 bits? 4 billion something, okay? So the number that does get pretty big, okay? The base where you're modding with get really big. But is this something that you have to think about when you write your programs? Absolutely. Absolutely. Let's say you're dealing with a program that calculates or deals with a national deficit, okay? And you allocate just an into it. What is our current national deficit? Okay, we can look it up, right? I mean, this is something that is easy to look up. So U.S. national deficit. And, okay, 18 trillion, okay? 18 trillion is 18, basically tera, right? Okay, can it be represented using 32 bits? No, cannot be represented using 32 bits. So if you choose the width of your integer where it cannot represent the value that you need to represent, you're encountering this problem because everything has an implicit mod 4 billion. Is that making any sense? And then most programmers will say, but that's okay because now we have 64-bit processors. Okay, so 64-bit means 2 to the power of 64 is a huge number. We will never run out. That's what they said about 32-bit numbers. And that's also what they said about 16-bit numbers when everything was 8-bit wide. Okay, so we will eventually run out of values with 64-bit numbers. And that's why as a programmer, when you use an integer, unless it is only for something that's really kind of simple, you always have to think about what is the range of numbers that I need to store in this variable or member, data member. Because if you don't think about that ahead of time, at some point it's going to bite you, or somebody who is unfortunate to inherit your code. Okay? All right. So modulus operation, kind of like that. What about signed numbers? What about negative values? We can only store positive values here. So it seems. Right? Are we doing okay so far with this analogy? Okay? Because what we are seeing at this point with that circle is from here and up to this part, and we are turning into a circle. But what about the other side of the number line, the negative side of the number line? We can do the same thing too. Why not? 0 minus 1 is negative 1. Negative 1 minus 1 is negative 2, 3, negative 4, negative 5, negative 6, and negative 7, and negative 8. We can certainly choose a different part of the number line and wrap that portion into a circle. Is that okay so far? Same concept, right? So now the biggest question is, but how do we deal with this, circle, so that the computer has a particular way of looking at things? Well, before we answer that question, let's just look at this particular representation and see if the calculations work out correctly. Okay? Because remember what I said? Positive 5 plus negative 5 should be 0. Remember I said that? Let's see if it works out for an 4-bit number system. Okay, oh, by the way, what is negative 5? How is it represented? Negative 5 turns out to have the same representation as 11 in base 10. So when you look at the base 2 representation, I'm going to use a blue color here for the base 2 representation. 11 is 1, 0, 1, 1 in base 2. And then 5, we already know that. 5 has a representation of 0, 1, 0, 1 in base 2. So now we want to add these two 4-bit numbers and see if we end up with 0. Okay? So I'll do that using the projector. Okay? And we'll go ahead and start a new calculation here, which is 1, 0, 1, 1. We claim that this is representing negative 5. And then we have 0, 1, 0, 1, which is representing just 5. Okay, so we'll do the base 2 calculations. And see if this works out. 1 plus 1 is a 0 with a carry. 0 plus 0 plus 0 is 0 plus 0 is a 0. 1 plus 0 is a 1. 1 plus 1 is a 0 with a carry of 1. 0 plus 1 is a 1. 1 plus 1 is a 0 with a carry of 1. 1 plus 0 is a 1. 1 plus 1 is a 0 with a carry of 1. So if you just focus on the 4 bits that you can represent, what do we get? 0. We get 0 back. So it does work out. It has to do with the way we look at the number circle. Yep.
So when we're doing this, we're just completely ignoring the last carry.
That is correct. The last carry or the last borrow is not considered as a part of the result. Because you can only store 4 bits, okay? It's just like, with a 64-bit number, the carry out of the most significant bit cannot be stored as a part of the number. I'm just, shrinking the numbers down to 4 bits because it's easier to visualize. And I don't have to write all the zeros and ones. Is that making any sense so far? Okay? So it also means in a modulus system, okay, if you take everything and mod it with 16, negative 5 is the same thing as 11. They work out the same way.
Should do that. Should try that.
Oh, let's try it. Okay, so let's try negative 5. Okay, so we'll say, what is negative 5 plus, let's choose a huge number here. Okay, so let's choose 72. Okay, and everybody can do this, right? Negative 5 plus 72 is 67. Okay. Oh, but 67 cannot be stored as a 4-bit number. We have to mod it with 16 first. 67 mod 16 is what? What is the remainder
3.
of 67 divided by 16? 3. Okay. All right. That's 3. And I claim that negative 5 is the same as 11, right? Okay, let's do it this way. 11 plus 72 is what?
83.
83. And what is 83 mod 16? It's 3 as well. So it works out exactly the same way. Okay? It has to do with the fact that adding is really just rotating this way, subtracting is rotating it the other way. And it doesn't matter how you label these individual points, there are only 16 points in the circle. Is that okay?
Yeah, why do they call it 2's complement?
Aha! They call it 2's complement for an interesting reason. Okay, so you're asking a question that is a really good lead-in, okay, from what we are talking about here. Okay, so this is called 2's complement. In other words, looking at -5 this way is the result of applying 2's complement. So let's talk about 2's complement. Okay, well, I'll go ahead and define what is 2's complement. 2's complement, and I'll use C2 of x as 2's complement. It's just a representation of the symbol. Okay, so C2 or the 2's complement of x is defined to be the 1's complement of x plus 1. And that's why it's called 2's complement. Okay? 1's complement is also known as bitwise knot. Okay? Okay, so let's check this out first, okay? Does it work out? I mean, this seems way too easy to come up with the representation of a value and take the negation of it, right? Okay, because it just involves a bitwise knot, and then you add 1 to the result of the bitwise knot. Let's check it out. So we'll go ahead and check out the 2's complement of 5, which is 0, 1, 0, 1 in base 2. Okay, what is that supposed to be? It's the bitwise knot of 0, 1, 0, 1 in base 2 plus 1. What is the bitwise knot of 0, 1, 0, 1 in base 2? 1, 0, 1, 0 in base 2 plus 1. And what is 1, 0, 1, 0 in base 2 plus 1?
11.
Yep, so it seems to work out. Oh, but the other way should work out as well. In other words, if you take the 2's complement of a negative value, you should get back the positive value. Because I'm claiming, this is a big claim, okay? I'm claiming in modulus arithmetic, using base 16 as a base, using any power of 2 as a base, 2's complement is the same thing as arithmetic negation. Okay, that's my claim. Okay, we'll check it out whether it works or not. So what I'm claiming is something that is really profound, because I am saying taking the 2's complement of x is the same thing as the arithmetic negation of x. Okay, now if that is the case, that means the 2's complement of 1, 0, 1, 1 in base 2 should get back to 5, or 0, 1, 0, 1 in base 2, right? Let's see if it works out. It is the bitwise knot of 1, 0, 1, 1 in base 2 plus 1. And some people can say, oh, I can see it's not working right away, but it does work out. So we'll take the negation of 1, 0, 1, 1, which becomes 0, 1, 0, 0 in base 2, and then we add 1 to it, and what do we get? We get back 0, 1, 0, 1 in base 2. So everything that you know about arithmetic negation, we can use 2's complement to do it. Are we still doing okay so far with what is 2's complement? Is that okay? All right. There's one really cool trick you can tell whether a number is negative or not. Because when you look at this number circle, this entire half has the most significant bit set. In other words, if the most significant bit is a 1, the number or the bit pattern can be representing a negative value if you choose to look at it as a signed number. Does that make any sense? Because -1 or 15 is 1, 1, 1, 1. Okay? The most significant bit is a 1. -8, which is also the same as 8, is 1, 0, 0, 0 in base 2. The most significant bit is a 1 as well. And everything in between will also have the most significant bit set as a 1. Are we doing okay so far? Yes?
Are negative numbers, they're stored as a 2's complement of positives? Is that what their pretty much negative numbers are? Always? When they're stored in the memory?
When they're stored in memory, a negative value it would use the 2's complement method to encode it.
But what is the value of 1000?
1000 can be 8, can be negative 8.
Like in
It depends on how-
a sign 4-bit integer.
If it is signed, it is negative 8. If it is unsigned, it is 8.
Thank you.
Okay, I can give you one more example that will make this kind of all clear. Yep, go ahead.
So with 2's complement, why are we negating it and then adding 1? What does that mean?
Because that is the same thing as subtracting the number from 250, well, in this case from 16, and then adding a 1 to it.
Why are we, why?
Oh, I take it back. It's the same thing as subtracting it from 16. Okay, 16 is the same thing as 0. So subtracting from 16 or subtracting from 0 means rotating in this direction the number of steps, which is the magnitude of the number.
Okay.
That's why it works out.
One-
Yep.
And in a 4-bit or an 8-bit, all ones would always represent -1 then,
Correct.
in a signed representation.
Using the sign interpretation, the bit pattern will be representing a negative value. So this is going back to representation. Remember the picture of the 7 samurai? Or Samurai 7, that's the name of the anime. A value is something that's concrete, okay? There are certain number of something that you see, right? A number, on the other hand, is just a way to represent it so that we can communicate with somebody else and convey, what is the quantity? And when we need to talk to someone, then we need to use a word to refer to the quantity. Is that okay so far? So depending on your native language, you can use there are many words to refer to the same quantity using just natural language. Is that okay? So you can use Vietnamese, Chinese, Russian, Italian, and so on and so forth. And every language has a word for the quantity, say 5, right? Okay. But when we use numbers, it's the same way. Okay, base 10 is just one language. Base 2 is another language. Base 5 is another language. You can have base 11 if you want to. It's just a really odd language that most people do not use. Doesn't mean that you cannot use base 11. So in this case, we're basically saying if you choose to look at things only as binary numbers, 2's complement is the same thing as arithmetic negation. Okay. So now we have a bigger question. Okay. The bigger question is, if I can see that the memory location has a content of something, how do I choose to look at the value? What is the value that is actually represented by that bit pattern? Okay. To answer the question, what I'll do is I'm going to use GDB to help us answer that particular question. Okay. So we'll write a very simple program. I don't need to store it, so I'm going to use temp folder for this. We'll just say char. Okay, this is the entire program. Int main, and I'll say char. The name of the variable is what is this. Okay, and I'll say what is this. Gets a particular bit pattern. So instead of using quote, quote, to refer to the ASCII code of a character or, the values in base 10, I choose to use hexadecimal because this way I am emphasizing the fact that I'm just using, it's a particular bit pattern, okay? But what exactly is it depends on how we look at it, okay? So I'll go to use a particular one, and I'm going to use, 6/8 in this case, okay? This is 6/8 in hexadecimal, and we already know how to convert from hexadecimal into base 2. So what is the base 2 representation of 6/8 in hexadecimal?
0.10.
And then That's correct. Okay, so it's a table lookup. Okay, you can do it much faster. The more you use it, the faster you can do it. But it's nothing more than just a table lookup. 6 in converting into 4 bits is 0, 1, 1, 0. 8 converting into binary as 4 bits is 1 and then followed by 3 zeros. Okay, all right. So this is my entire program. And you look at this program, go like, wow, that's a pretty pointless program because we declare a local variable, what is this, and then we choose not to do anything with it except to give it an initial value, and then we return from main. Okay, but we'll have fun with this program. So gcc-c-g char.c, because I don't want to see the warning message. char.c. And then we'll say gdb char. List the program. Oh, I can see why, because I should have done this instead. There we go. Okay, now we can list the program. We'll put a breakpoint on line 6, and then just run the program. So when you say print, what is this? What do you think it's going to print? Well, let's take a look. It says it is H. Well, let's see whether it makes sense or not. 6-1 is lowercase a, okay? So 1, 2, 3, 4, 5, 6, 7, 8, A, B, C, D, E, F, G, H. H makes sense, okay? So that means, 0, 1, 1, 0, 1, 0, 0, 0 can be interpreted as the ASCII code of H. If you send that particular bit pattern to a teletype terminal, it displays the lowercase h character on the terminal. Makes sense, right? Would you rather have the terminal display h, lowercase h, or would you rather have the terminal to display 0, 1, 1, 0, 1, 0, 0, 0? Well, we are humans, right? We learn how to read the alphabet, so to us, h is easier, okay? Okay, that's one way to look at it. But in GDB, you can also force a way to look at a number, okay? So we'll do a /x here, which means we're looking at a number in hexadecimal, okay? Is that surprising to you? That, what is this as a variable, as an 8-bit variable, can also be represented as 6/8 in hexadecimal. Is that surprising? No, because the program used 6/8 in hexadecimal to initialize it. Yep, go ahead.
What is the 104?
The 104 is the base 10 representation. So you can force a base 10 representation using a /d. Okay, it's 102 because it's 6 times 16 plus 8. 6 times 16 is 96. 96 plus 8 is 104, is 104. Okay, and we can push it one more step. We can say, hey, I want to look at this as a binary number. Okay, /t will show you a binary number. Sure enough, it is there's an implicit 0 as a leading 0, so it's basically 0, 1, 1, 0, 1, 0, 0, 0. Okay, all right, cool, but it doesn't have a negative value. It cannot be used to represent a negative value. Why? Why can't 0, 1, 1, 0, 1, 0, 0, 0 represent a negative value?
It's unsigned.
No, /d is using the signed interpretation already. What is the most significant bit? What is the bit to all the way to the left-hand side?
0.
It's a 0, okay? And if you look at this chart here, everything that has a 0 as the most significant bit, these are 4-bit numbers, are representing non-negative values, right? I have to say non-negative because 0 is neither positive nor negative, or can be seen as both. But when you say non-negative numbers, it will certainly include 0.
But wouldn't negative 15 be represented on the right as well? So under the 1 would.
Yeah, but the most significant bit is a 1. I was asking, when the most significant bit is a 0, what are the values? Well, they go from 0 to 7, not 8. Okay, not 8. All right, so if that is the case, let's do something fun with this. So we will say set var, what is this? And we'll change it to a particular bit pattern. FF is an easy one, so we'll do FF here, okay? So 0xFF doesn't really tell you how to look at the number. All it's specifying is 1111, 1111. So as far as the computer is concerned, it is just a byte that has all the bit positions being ones. Okay? It doesn't say a single thing about what it is actually representing. It is just what it is storing. Okay? All right. So we'll redo all the experiment. The first thing we do is just print it. Okay? In this case, it shows you it is \377 as a character. Okay? In single quotes, it would be a character. That's because it does not correspond to any character in the ASCII code set. So this is one way to represent a character, an 8-bit character that does not have a interpretation using the ASCII table. Okay, that's one. We'll choose the second way to do it, which is with a /x, which is printing the same thing but in hexadecimal. Not very surprising, okay? Kind of boring, in fact. And then we'll choose to look at it as a /d. A /d means look at this as a signed value, okay? And should not be very surprising, it's -1. And the last one is to look at it in decimal, but this time look at it as an unsigned number. It is 255. And, well, actually I lied. There's one more, /t, to look at it as a binary number. Okay? What do you think you should be getting? All ones, 8 ones, right? Okay? So, okay. So what are we dealing with here? We are basically saying the same bit pattern can be seen as a character that cannot be printed because it's not a part of the ASCII code set. It can be seen as FF if you choose to use base 16. Can be seen as 1111, 1111 if you choose to use base 2. Can be seen as -1 if you choose to use base 10 as a way to print it out, but using the signed interpretation. Can be seen as 255 when you choose to look at it as an unsigned number. It's the same bit pattern. We're looking at exactly the same byte location, but we can choose to interpret it in different ways.
Well, how will we know when 4 ones or 8 ones represent 255 or -1?
Well, that's a very good question. Let me just repeat the question so it's recorded. Okay. So the question is, let me see if I can paraphrase your question. The question is, how do we know what to see as, during the execution of a program? Well, that is one of the biggest mysteries and also one of the biggest source of problems in this class. Okay, because the way you deal with this in C is entirely different from the way you deal with it in assembly language programming. Okay, and I'll illustrate the first one. Okay, we haven't really seen the programming languages or the assembly language programming method yet. So what I'll do is I'm going to go to the same program, which is char.c, and I will I'll give you another one, and I'll say, well, since I have this variable, I'll have that as the other one. I know these are totally awful, names for variables, but since we're on a roll, so we'll go ahead and do this. Okay. Yes.
Since you define both of those as characters, how come we could print them out as something other than characters, like as base 10 or base 2 numbers? Since you defined what is this and what is that as characters,
yeah,
how come we can print them out as something other than characters when you run the program?
Because I use the slash to force interpretation, to force the printing, option. So I can see. Okay, let's see. Let me repeat this step here because I forgot the -G. It won't debug without the -G. Okay. This is the program. We'll put a breakpoint on line 8. All right. So here's the fun part. Okay. We'll just do a whole bunch of printing statements. But before we do a whole bunch of printing statements, people will be. I know like about 60% of this class is now thinking at least, how do I know what I can do with print? Well, can someone say help? Yeah, it will take you some time to read it, okay? But nonetheless, I think this is something that you guys can read. So I leave it up to you guys to read it. The most important part has to do with the formatting, okay? Expression can be preceded with /FMT, where FMT is a format letter but no count or size letter. See X command. Great. It has a reference to the X command, so what do? You say help X. So help X will now tell you that you can use the format FMT, can use the following interpretation: O for octal, X for hexadecimal, D for decimal but signed, U for decimal but unsigned, T for binary, F for float, and so on and so forth. The other ones do not really apply in this case because we only have 8 bits or 1 single byte, but you can choose to look at it in different ways. These are the formats, okay? All right, so what are we doing? We want to run the program. We get to the breakpoint, so we'll say, what is this? Okay, it's H. What is that? What is that? It's 377, but the 377 is in what base? Come on, quick.
10.
It's not base 10, because if it were base 10, it would be 255.
Why is ASCII code?
I know, but 377 is a number in a certain base. What base do you think is in? It's in octal. Yep, it's a base 8 number. 1111, 1111 is a binary number. In octal, it is in 377. Okay, all right. Are we still doing okay so far? Okay, but yeah, go ahead.
No, that's
Okay, but the biggest question is, how do we know when to use what interpretation? That was the question, right? Okay, so let me see if you guys can answer this question. What is this less than what is that? Okay. What about this? What do you think about this comparison? Should it return a 0, which means it is false, or should it return a non-zero, which means it is true? What do you think?
True. No.
It should be false because 377 is bigger.
Because char is implicitly signed. Okay? So if char is implicitly signed, when you compare, you'll be comparing two numbers interpreted signed. As signed numbers, you're comparing 104 to -1. So now the question becomes, is 104 less than -1? And the answer is false. Okay? So we'll see whether it gives us a 0 or not, and sure enough, it gives us a 0. Okay? But in C and C++, and you can do this in GDB as well, is you can force interpretation. In other words, you can say, oh, I know this is an unsigned char. Okay, you can do a typecast. So we'll go ahead and do a typecast on both sides and see what happens this time. So we say unsigned. I cannot type char on one side. Oops. On the other side, we'll do the same thing. Okay, unsigned char. All right. So in this case, we are typecasting what is this, and we're typecasting what is that. And in both, we are typecasting both of those to unsigned interpretation. The unsigned interpretation of the bit pattern of H, which is 0, 110, 1000, will still be the same as 104. Okay? The unsigned interpretation of 1111, 1111 is going to be what? 255. So now the question is 104 less than 255? The answer is yes. So it should give me a non-zero number. Not necessarily a 1. 1 is the one of many values it can give me, but in this case it does. Okay? So that is answering your question. Okay? When do we know which way to interpret it? In C and C++, it's easy. Okay? It's automatic, because the type of a particular location in memory is associated with the variable itself. So whenever you use the variable in comparison, it automatically knows whether I should see it as a signed or an unsigned. But that is also the greatest source of problem in assembly language programming. Because in assembly language programming, there's no such thing as type. So when you refer to a byte, when you refer to a memory location, you're referring to just the memory location or the content of the memory location. Most instructions do not care how you want to see it. Is this a character? Is it an ASCII code? Don't know. Is this a signed number? Don't know. Is this an unsigned number? Don't know. Or is this a pixel? Don't know. And don't care. Okay? And there are only very few instructions that really care because it does matter which way it should be interpreted. Okay? But most instructions do not. Is that answering your question, or is it actually prompting more questions?
It's prompting more questions.
Which is good. That's the way it's supposed to be.
It's prompting an office hour visit.
That's fine, or we can talk about it in the lab too. Or if you think the question is going to be relevant to the entire class, go ahead and ask it in class. But I think you might need you need some time to formulate the question. So I'll leave it up to you to kind of formulate the question first. Are there any questions from the rest of the class? I'll give you guys a little bit of time to formulate your question. No questions? Or do you need more time to formulate the question? No question at all?
I have to revisit this video and then ask.
Okay, that sounds reasonable. The only one I do not know what the answer is going to be is what happens if you only cast one side but not the other side. Okay, that is the only one that I do not know what is going to be the answer. In other words, if I cast only the other side to unsigned char, and the first one I do not cast it, well, because the first one doesn't matter whether it's casted or not, right? And if I cast only the first side and not cast the other side, it'll be a 0 because the right-hand side is representing a -1. Okay. All right. Any other questions?
Is this going to be on the test? Is this going to be on the test?
Oh yeah. This is very, very important in assembly language programming or in any type of low-level class. Okay, computer architecture. Even in C and C++, this is a very important concept because how do you know what this is? Okay. Let me see if I can give you another example. I'll give you one example here. I'll just draw something on the whiteboard, and I'll ask you what do you think it is. Okay.
Circle.
Okay. What is this?
Number
0.
Okay. 0 is one way of looking at this. What is the another way? Huh? Looks like an egg to me. A little bit.
Cantaloupe.
Cantaloupe.
A cantaloupe. Okay. It can be seen as a big uppercase O or a lowercase o or a 0. Okay? But that's the same thing as the content of one byte location. Is it 255? Don't know. Is it -1? Don't know. Is this just representing, a part of a pixel? Maybe. Okay? It really is just literally 1111, 1111. Okay? In other words, you don't know how to deal with this byte location until there's a context to make use of this content here. Okay? In other words, if you look at this symbol here, okay, if I add on if I provide the context, then you know what it is supposed to be, right? Because the context says, oh, this is one of the letters of a word. Okay? Or if I say this is a different context. The context helps you, interpret what this is.
How do we find out that context via?
But by itself, you don't have a context. So when you look at a memory location that has this content, it has no context whatsoever to really tell you what it is. So it's until you have instructions to act on the content, then you may have the information to say, oh, okay, this is a signed number, or this is an unsigned number. Yep.
So would we just test it by plugging it in, or?
Well, by the time we get to instructions, you will see there are only very few instructions that has a inherent way of looking at a location like this and say whether it's signed or not. Okay, very few. Most instructions do not need to know what it is. Okay, most instructions will just say, oh, this is a byte and it has all ones. And that's all it needs to know. There's nothing else it needs in order to do that. Because if I give you something like this and say, can you copy this on a piece of paper? Do you need to know whether this is an uppercase O or a 0? No, you just draw on a piece of paper the same shape and you're done. It's the same thing, okay? So if I want you to erase this location, do you need to know what this is representing? No, because erasing doesn't really care, doesn't need to know what it is. It's just erasing it. Same thing. Okay, so many operations you can perform to a memory location do not need to know what it is. You're just doing a particular operation and it's just operating on the bit level. There are only very few instructions that need to know, okay, is this signed or not? Or I'm going to assume this is signed. Multiplication is 1. Because signed multiplication is different from unsigned multiplication. So with multiplication, there are 2 instructions. One to do signed multiplication, which always look at memory locations as signed numbers. And the other one is unsigned multiplication, which always look at memory locations as unsigned numbers. But those are the very few instructions that actually has a forced interpretation of memory locations. Yep.
So you would define it not by the type, but by the method?
Exactly. It is associated, the meaning of a byte location is now associated with the instructions, but not with the type, because there is no type. Okay, that's a very good point. That's exactly what it is. So you can also look at this as a deferred interpretation or deferred assignment of meaning. In other words, until you actually get to do something at the memory location, you don't need to know what it is. As opposed to C and C++, what is the first thing you do when you declare a local variable? Exactly. What is the type of this thing? So you know from the moment you declare a variable, it has a type. It has a particular way of, this is how you look at this. Okay? I can give you even more examples if you want to. Okay. And this is also somewhat relevant to this class, and most people who talk this, who watch the video will go like, no, we don't want to talk about this. Yes, we will talk about it. Okay, so I'm going to talk about that, the dreaded topic of this class. We'll get there. So we'll say float x, and x equals to, say, 300, okay? Nothing too nasty. Or is it? Okay, so we'll take a look at this one here, and we go GCC dash, I'm getting a little bit lazy, so I'm just going to combine all the steps into one. Okay, GDB float. Just the program, put a breakpoint on line 6, run the program, and we want to print what is x, okay? So when you say print x, it will use the default type of x. How does GDB know, hey, x is supposed to be a float, we should print it out as a floating point number? Because it understands C code, okay? When we specify the -G, it generates a simple table entry that GDB can read. And GDB is pretty smart, okay? GDB can read the symbol table and go like, oh, x is a local variable, it has a type of float. So unless you force the interpretation to be something else, it will always say, oh, okay, I know how to print out the value. represented by these zeros and ones. So not very surprisingly, it gives you this. Then you might think, oh, okay, so I think we know the binary representation of 300. Let's check it out, okay? So we'll do a /x in base 16 first. What is x, okay? Okay, let's check this out first. Just mentally check it out, okay? So in theory, 256 plus at least the 32, and what else is there in 300? I cannot do my base conversion that quickly. Plus 12, I think it's a plus 8 plus 4. Is that right?
Yep.
Okay. So we are looking at a number with 0, 0. I'm working from this end because I have to work from that side. 1, 1, 0, 16, 132, no 64, no 128, 1, 256. And then the rest should be zeros. Okay? That's how we represent 300 as an integer in base 2. Is that okay? So when you look at this as a hexadecimal number, we have 1100 here, which is a C, and then we have 0010 here, which is a 2, and then we have basically a 1 here, and then all zeros on the other side. So 12C in hexadecimal is 300. Let's check that first, okay? So we'll say print in decimal representation, what is 0x12C? It is 300. So if I print x, hey, maybe I should get that. But what are we going to get? Oh, it does. We do get that. That's not right. Oh, I know why. Because I'm forgetting this part here. I have to cast it into an integer first. Because as a floating point number, it is 300. It's still working. I can fix that. That. Now it works. Okay. So I'm taking the address of x and then dereferencing it at the end. So you might think asterisk and ampersand, they cancel on each other. What is the whole point? But I have a typecast in between. So I'm taking the address of a floating point number, cast it into it, point it to an integer, and then dereference the pointer to an integer. In other words, in the process, I made GDB lose track of how it is supposed to interpret the bit pattern at that location. And I'm forcing it and say, look at this location as an integer. Okay? And it is not what you're expecting. That's because it is a floating point number. Okay? What is the actual bit pattern at that location? Let's check it out too. Okay? So when you print it with a /t, this is the actual, content at that location. It's not quite 32-bit. I think it's, some leading zeros are missing, but that's basically what it is. Okay, that's the actual location or the content at that location. The other way to look at this is to use the X command. I'm gonna show you this one too. WT's. Okay, there you go. That's a better way to look at it because it includes the leading zero. This is actually what is stored at the location. The variable x in that program has this particular bit pattern. Okay. Yep.
In hexadecimal, is 0x, is that always going to be 0x, or is there?
0x is a prefix to indicate the rest is a hexadecimal number.
Okay.
So it's just a prefix. Yep.
What is type flow? What is type flow?
What is type
flow?
She's asking what
Is
a
it
floating
like integer?
integer is.
Well, we'll see that in this class too, and I'm not going to spend too much time to talk about it today because we will get to that. But this is totally related to what we are kind of talking about at this point. So if you go to non-integer representation, it will talk about floating point numbers. Okay. But this means there are many ways to interpret the content at a location. Are we still doing okay so far with the concept of a signed versus an unsigned number? Okay, all right. And that's pretty much it, okay? we talk about subtracting and comparing. Okay, now that is kind of interesting because when you look at subtraction, it doesn't really care whether numbers are signed or not. Okay, we'll take a quick look here. So we'll go back to our slide here and let's do some subtractions. Okay, and we'll use 4 bits. Okay, just because it's easy to deal with. Yep.
The roll sheet.
The row sheet, I almost forgot. Okay. So we'll deal with 4-bit subtraction, and you guys can give me some numbers to subtract. We'll take a look at what happens when we perform those subtractions. Okay, so give me 2 numbers that can be represented signed in that number wheel. Okay, and we'll do some subtractions. Give me something that works and something that does not work. In other words, give me a case where the result can still be represented in the number wheel, and give me one case where the result cannot be represented in the number wheel. First one is it can be represented.
5 plus 5.
5 plus 5. Well, that actually falls into the second category. 2 plus 3, okay, that will work. Okay, so 2 plus 3, subtraction, okay, not addition, subtraction. 2 minus 3, okay, how about 2 minus 3? Okay, so we'll do a 2 minus 3, okay, and see what happens. All right, so this is also a good practice for those of you who, worked on your subtractor, okay. 0 minus 1 is a 1 with a borrow. 1 minus 0 is a 1. 1 minus 1 is a 0. 0 minus 1 is a 1 with a borrow of 1. 0 minus 0 is a 0. 0 minus 1 is 1 with a borrow of 1. 0 minus 0 is 0. Oops, 0. 0 minus 1 is 1 with a borrow. Okay. So when you look at the actual result of the subtraction, it's 1, 1, 1, 1. The extra borrow cannot be represented as a part of the result. It is on its own somewhere. Okay? So 1, 1, 1, 1 is the result of the subtraction. Does it make sense? 2 minus 3 is negative 1. It does work. Okay? So now we move on to the case that does not work. 5 plus 5 doesn't work, but we're dealing with subtraction. So what about...
Why doesn't 5 plus 5 work? That just gives us 10.
But 10 is the same as negative 6. When you choose to look at the 4 bits as a signed number, you can only choose one system. It cannot be represented negative 6 and 10 at the same time. So when you choose the signed interpretation, that bit pattern is negative 6.
So then we're only dealing with the right side of the wheel then? In terms
No,
of
we're only dealing with one interpretation. So anything that has the most significant being a 1, it has to have a negative value. It has to represent a negative value. Okay. Give me a case where it doesn't work. Subtraction.
Minus 8 minus 1.
Minus 8 minus 5. Okay? So negative 8 minus 5. Negative 8 is this. Minus 5 is that. Okay? So let's see what we get here. All right. 0 minus 1 is a 1 with a borrow of 1. 1 minus 0 is a 1. 0 minus 0 is a 0. 0 minus 1 is a 1 with a borrow of 1. 0 minus 1 is 1 with a borrow of 1. 1 minus 1 is a 0. 1 minus 0 is a 1. 1 minus 1 is a 0. Okay. So it's telling me that negative 8 minus 5 is 3. Doesn't make a sense. Doesn't make any sense to me.
negative.
No, it's not
Oh.
negative 3. It is supposed to be negative 15, right? Or negative 13. But negative 13 is, this is negative 8, negative 9, negative 10, 11, 12, 13. But we cannot see that as a negative 13 because the most significant bit is 0. Clear. Yep, 0. So in the second case, we have a subtraction, but unfortunately, we only have 4 bits, and therefore we cannot represent the value that we need to represent. Is that okay so far? But what about the the unsigned interpretation? Does it make sense in the unsigned interpretation? What is the unsigned interpretation of 1, 0, 0, 0? It's 8. 8 minus 5 is 3. So it does work out if you choose to interpret the values as unsigned. Are there any questions about all this stuff here? Are there any questions about 2's complement? Because everything stems from representing, or doing arithmetic negation using 2's complement. That really is the key to all of this stuff here. But the downstream consequence is actually very important, because remember the adder that we worked on, the subtractor that we worked on. We can keep those, even though we can now deal with negative values. We don't need any special circuit to deal with addition or subtraction. So that's the good news. Okay, so this particular way of looking at numbers in the negative way, or looking at negative values, does not require new adders or subtractors. The mechanism of adding and subtracting does not really matter. What does change is comparison. How do we compare numbers? Okay. How do you do comparison? Subtraction. But now we say that subtraction is the same whether it is signed or unsigned. So what is going to indicate, excuse me, what is going to indicate whether the first number is larger or representing a value that is larger than the value represented by the second number? How can we tell? This is why we have this note here. Okay, so we have binary subtraction. The first part we have talked about already, so don't worry about that part. The second part is the most important part. We have certain things called flags, okay? And these are flags that are internally maintained by a processor. There are 4 important flags when it comes to this class. There are more flags than this, okay? By the way, there are 32 flags in the flag register. But these 4 are particularly important. There's the carry flag, which is also known as the borrow flag. That one we know already, okay? That's not a big deal. The 0 flag is fairly easy to deal with. The sign flag is just the most significant bit of a number, of a binary number. So the first 3 are pretty easy to deal with. The overflow flag is the one that will give us some trouble, because that is the one that always look at numbers as signed. Okay? And overflow has a certain meaning. Okay, so we'll deal with these particular sections on maybe Thursday, depending on whether we have time to deal with this, because on Thursday I want to finish up the processor control unit, because I want to show you all the pathways between the register and the memory bus. But if we do have time on Thursday, we'll be dealing with this part here. Okay. So you want to read ahead of me, even if you don't fully understand all of this stuff here, read ahead of me, so that by the time we talk about this, you have some idea of what it is, and you can bring up the questions. So you guys have reading assignments, up to here, okay, on this particular slide, and also kind of just take a quick look at the processor architecture itself and figure out, how things are connected to the memory bus. Okay, what is connected to the data bus? What is connected to the address bus? That's the end of today's lecture. I will go to the lab to answer additional questions if you guys have any questions.